when we study the motion of a particle, it's often very convenient to resolve the acceleration into two components. The first being the direction of the tangent, and the second being in the direction of the normal. Um, what does this mean? Well, let's draw a quick picture. I have some space curve, and I have a particle at this point, so I can think in terms of r of t, whatever. I don't want to draw that initial vector in there. Let's see. Yeah, forget that initial vector. So it's moving in this direction. Okay, so it has a tangent component and this normal component, which we can figure out. Well, when we think in terms of acceleration vector is going to be like somewhere like this. And I can resolve this, if this is my acceleration vector, into these components. So in other words, I would have something like, let me see if I can draw this out. Oops, I missed the vector. Make it a little bit longer, make it fit. There we go. Just make it a big head. There we go. So acceleration vector is going to have this component along the tangent and along the normal. So that's really what we're heading for, what we're trying to do now. Now recall that the unit tangent vector we typically use t for, and I'm going to make it obviously a function of t, and this is a vector. Even though whenever I write this capital T, you should know right away I'm talking about the unit tangent vector. This is being defined as r prime of t divided by the magnitude of r prime of t, which should make sense because if r is my position vector, r prime of t we're thinking of as being the rate of change, so right away we're thinking it's tangent, right? But because this is a unit vector, I'm simply going to divide it by the magnitude of the first derivative of the position vector. And when I divide any vector by its magnitude, any non-zero vector by its magnitude, I get a unit vector. So this should make sense as a quick review that this really would be a unit vector, specifically the unit tangent vector. But this is actually the same Well, remember that first derivative is velocity, so it's really the same as the velocity vector, and again these are vectors, divided by the magnitude of the velocity vector, which we could write as the velocity vector divided by v. I'm using v to represent it's a function of t, but it's no longer a vector. Therefore, this unit tangent vector is really equal to the velocity vector, that's a t, over v, which would then imply that velocity, the vector, can be written as the magnitude of the velocity, v, times the unit tangent vector. Well, if you stare at this for a second and try to wrap your mind around what's that saying, that actually makes a lot of sense, because v is the magnitude of the velocity. So if I take the magnitude of the velocity and I multiply it by a unit vector that's going in the same direction as the velocity, then that is the velocity vector. So that should actually make sense. That result shouldn't really be much of a surprise. Now, I can take the derivative of both sides. So if I now take ddt of both sides, I'll have ddt of the velocity vector, again it's a function of t, which is going to be equal to ddt of vt. Remember, this is a vector, this is not. But it is a function of t. V is a function of t. So what that is telling me, that v prime is going to actually be equal to, if I take the derivative of the right-hand side, I'm going to have v prime t plus v t prime. It's just a product rule because both of these are functions of t, vector, non-vector, but still functions of t. But remember, the first derivative of velocity is acceleration, so that gives me that the acceleration vector is actually equal to v prime t plus v t prime. Now, recall that curvature, we use kappa. We define curvature as being the magnitude of the first derivative of the unit tangent vector divided by the magnitude of r prime of t, the first derivative of the position vector. But that I can write as the magnitude of t prime over, well, the first derivative of the position vector is velocity. The magnitude of it is the magnitude of velocity, which is also known as speed. But that's my v. Therefore, I can say that the magnitude of t prime is equal to the velocity times the curvature. Now, don't forget again that this v is a function of t. It's not a vector, but it is still a function of t. And obviously k is a curvature, it's a scalar, but it's also a function of t because these are all functions of t. Now, from here, recall that the unit normal vector n, this is the unit normal vector, is actually equal to t prime over the magnitude of t prime. That's the unit normal vector pointing in toward curvature with length 1. Therefore, I can say that, let's see, t prime equals the magnitude of t prime times that normal vector. But that, see right here, t prime is right there. That's going to be equal to the velocity as a function of t, but not a vector, times the curvature times the normal vector. So this may seem like a bunch of mumbo jumbo, but actually we just did a couple of really important things. We now have acceleration that equals v prime t plus v t prime. That's right there. But now I can rewrite this as being equal to v prime t. Again, this is a function of t, but it is not a vector. Plus, well, t prime is right here. So this is v times v kappa n, which of course I'm not going to leave it like that. I'd write this as v prime t plus, of course, n's at normal vector, v squared kappa, which is a curvature, n. This is actually pretty important because, I will make this a smaller v, this little v. This right here, v prime, this is the tangential component. This right here is the normal component. That is really extremely important because now if I go back up to this diagram I did earlier, I know what this component is. Here's a tangential component, and this is the normal component. So I can think of those, or I can resolve acceleration into those two components. Now, one of the things you may notice right away is that b is missing. If b was in there, the binormal vector, then we'd actually be dealing with the t and b frame. But we don't. We're dealing with just t and n, not b. So the binomial vector really doesn't play a part when we're talking about acceleration. And really, this makes sense because if I draw that picture again, see, I'm going to have this space curve. And here's a particle moving along the space curve. And I have this acceleration vector. And this acceleration vector is going to have a component. Let's see, here's my tangent vector, my unit tangent vector. Here's my unit normal vector. So this acceleration vector is going to have a component in this direction and a component in this direction. This, like I said, it does make sense because acceleration takes place in the Tn plane, which you've come to love and adore as being the oscillating plane. The idea that acceleration is taking place in a plane at any time t should make a lot of sense. Now, obviously, as I think about 3 space, and if I look at the T and B frame, the T and B frame can be twisting around as in 3 space this curve is moving and twisting. But at any time t, acceleration will be planar. It's not going to be moving in 3 dimensions. So this idea actually does make quite a bit of sense. Now, very commonly, we use the component in the direction of the unit tangent vector. We use a sub t to represent that component, and a sub n to represent the component in the direction of the unit normal vector. That means a sub t equals v prime, not a vector, right? And a n equals v squared kappa. Because remember, acceleration equals v prime t plus v squared kappa, where kappa is a curvature, n. Here is the tangential component. That is a t. And here's the normal component, which very commonly we simply do is a n. So we will commonly write the acceleration vector, make it as a function of t now if we want, as being at t plus an n. Now notice here that this tangential component is the rate of change in speed. And this normal component is actually a function of speed squared and curvature. And if we attach that to physical phenomena, that really makes quite a bit of sense, because think of driving a car around a curve. So we have this curve. And here you are in your car and you're zipping along this curve. Now, staying on this curve, the faster and faster I go, the more you feel like you're slammed up against the side of the car. So the stronger this component is going to be. So as I increase the velocity, holding curvature constant, this component gets bigger and bigger and bigger. Now, likewise, if I go just the opposite and say, okay, I am going to hold the velocity constant, but I take this curvature and I make it more and more curved. So in other words, I'm going to make a sharper and sharper turn. You can make a wide turn at 25 miles an hour, piece of cake. Make it really, really, really sharp, and you're going to lose it. So that's really what this is saying. And when you attach it to that type of physical phenomenon, then these components actually start to make a lot of sense.